wonderful site. You see that these are where you get the links to the various class videos, or you can just go to YouTube. But every quiz that we've taken has quiz solutions in here. So if you're questioning anything about the quiz, or you missed a quiz and I gave you back a blank quiz and you just want to see how you did, you can check them here. And also, I wanted to show you that at the end of chapter 2 in your textbook, as most textbooks have, they have a chapter test, and there's 34 questions. And if you work through some of those questions and you have difficulty, there are actually chapter test videos in my math lab, but so you don't have to go out looking for them, I gave you the link right here. So let's suppose you're looking at the chapter test exercises and you have a problem with number, say 9. You just come right to this link and you go right here to exercise 9, you click on it, and you're going to see a video. I won't wait for it to all come up, but you'll get a video that shows you how to actually work through that particular problem. Okay, so I'll just wait, see if it says playback trouble. So you just hit play and it should come up here in a second. It's loading. I don't know how long it will take to load. So let's see. Still loading. Chapter test prep. So play. So here they're doing a piecewise function, and they take you through that particular piecewise function. Okay. So I don't want to wait for this. Oh, let's see. So if you have trouble with that, you just come to this video. Okay. So all 34 problems have videos that go along with them. So that's kind of cool. Okay. So that's what's available. Your study guide that you have back there that I gave you on Monday is available here as well. You also have, just like on test 1, we had that test 1 homework, extra homework problems that was ungraded. We have a test 2 with lots of problems in it as well. So there's no problem finding problems to work on to prepare for the test. The main problem you would have is finding the time to do it all. So remember, you got the study guide, you've got the chapter 2 problems with the videos, and then you have those homework problems in the My Math Lab. So today we're going to start chapter 3. This material is not going to be on the test Friday. It's for your next test, and the homework on this is due next Wednesday, as it usually is. Okay. So what's the date next Wednesday? The 6th, Wednesday, November 6th. Okay. And don't forget Tuesday's advising day, and I'll talk to you more about that on Monday. Okay. So let's take a look at quadratic functions. I think some of you may be familiar with this if you've had a Math 096 or 106 class here, then you've seen some of this stuff before, and it will be a bit of a review. But some of you haven't seen this stuff before. So you want to start us off, Cameron? Okay, so why do we have this condition that a can't equal 0 on this? Right, so if a was 0, we wouldn't have a quadratic, we'd have a linear function, right? So that's the only stipulation other than they have to be real numbers. A can't be 0. Okay, what's a parabola look like? So if I had the Cartesian coordinate plane right here, what would a parabola look like? How would you describe it? The shape. Like a U, yeah, okay. So it could look like this, look like that, okay. Go right through, our parent function looks like that, goes right through 0, 0, right? Okay. So some people refer to it as cup shape, some people say U shape, okay. I usually say happy face and sad face, right? The parabola is open, if the parabola opens upward, or it can open downward. Okay. But a quadratic is a polynomial. So a quadratic function is a polynomial function because all of your exponents are 0, 1, 2, 3, 4, really nice, friendly exponents. No even roots that you have to worry about. The domain, nothing in the denominator. So the domain for all of your quadratics, the domain is always going to be all real numbers from negative infinity to infinity. No restrictions on what numbers can go into a quadratic, okay? Because it's really a nice looking thing. Nothing to worry about. Okay, so x squared, I think we know f of x equals x squared is what we call our parent quadratic function, right? It's our one from which we do all kinds of transformations to. And we know that the point 0, 0 is located on our parent function. And most of you refer to 0, 0 as the origin, and that's true. But when it's when 0, 0 is on the function x squared, it has another name. It's called the vertex of your parabola. So this is also called the vertex of your parabola. Okay. And notice what happens when your vertex is located on a parabola that opens upward. Everything to the left of your vertex on the interval before your to the left of your vertex, your function is decreasing. So the function is decreasing for all x values to the left of 0. So on the interval negative infinity to 0, your function is decreasing. And your function is increasing once you take a baby step to the left of 0. So from 0 to positive infinity, that entire function is increasing. So the vertex is sort of this critical point in the life of this function. It's the turning point. It's where it changes, in this case, from a decreasing function to an increasing. Okay? So sometimes people like to call that the turning point. Okay? All right. Also, what could you tell me about this value? F of 0 is 0. What can you tell me about that value in terms of comparing it to all other values on this function? What can you tell me about the 0? The y value of 0. How does that compare with all other y values? Any other solution, any other point on that parabola? Logan? It's the lowest point, right? So this value of 0, this output or y value of 0, is the minimum value of that function. So that's the minimum value. So your range would start, your domain for f of x squared, for f, is all real numbers. And your range of f starts at 0 and goes to infinity. So 0 is your minimum value. Minimum. Okay, so that's just a little intro. That's not exactly what we're supposed to do right here. We're supposed to be talking about and a little review of transformations, since you're going to see transformations on Friday. So we're taking x squared and we're doing some stuff to it, right? We should know from looking at that, the equation for g of x, what transformations have happened to g of x. But first, Mary, do you mind getting that door for me? But first, let's just identify some key points on our parent function, and then we're going to perform a series of transformations and see what happens to those points. So we've already identified one key point. One key point is 0, 0. So let's pick a couple of points on either side of 0, 0. So let's pick negative 1, 1. Let's pick negative 3, 9. Okay. And then similarly, let's do 1, 1 and 3, 9 on this side. Okay. So there's just 5 points. I could have picked any 5 points. There's no reason why I'm selecting those particular points. So let's determine where these points go when we transform the graph of f into g. Well, first of all, look at the equation in g. How many actual pieces or transformations have we done to x squared? Just the number of them. How many transformations will we do to x squared to arrive at that particular equation? How many? 3. Okay, so let's identify the 3 transformations we're going to do. So if I'm just going to go down and make these points vertical for myself because I got a lot to write here. Okay, so we're going to do 3 transformations to get to arrive at our final destination. 1, 2, 3. So let's see what those 3 transformations are in the order that we're going to perform them. And hopefully these 5 points will allow us to get a nice quick sketch of the quadratic. Okay. So if you look at the equation for the function, and it says 2 times quantity x minus 1 squared take away 3, what's the first transformation we're going to do here? What's the first transformation? We're going to shift our graph to the right 1 unit. Okay, so this tells me I shift to the right 1 unit. And what does that mean in terms of what I do to each of these points here? I add 1 to all my x values. So I add 1 to all x values. That does the same thing as shifting that entire graph to the right 1 unit. So if I add 1 to -3, I get -2, I get 0, 1, 2, 4. My y values stay exactly the same, 9, 1, 0, 1, 9. So there's the first part of my transformation. And I could do this, I wish I had animation and I could just sort of keep moving, having this graph show each transformation, but I don't, and I don't want to take the time. So we'll do all of them and then graph the final transformation. So I've taken care of the shift right 1 unit. What do I do next? I did my horizontal shift. Now what do I do? Take care of my horizontal shifting first, and then what comes next in my transformation series other than atom? Stretching or shrinking. And where's that happening, Beth? What kind of stretching or shrinking am I doing here? It's going to be the vertical, yep. And where is it, the 2 or the it's the 2. So what kind of stretching am I doing here? You said y. What do we refer to that? Vertical or horizontal? Vertical. So we're going to do a vertical stretch by a factor of 2, which means all of our y values are vertical. All of our y values are multiplied. So multiply all y values by 2. Okay, we can do that. So now our x values are staying the same, -2, 0, 1, 2, and 4. Boom, 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 boom. And now all our y values are doubling. So 9 becomes 18, 1 becomes 2, 0 stays 0, 1 becomes 2, and that becomes 18. Okay, whew, almost done. And now what's the final thing I have to do that's outside of all of this stuff, all of that first term, the first term being this whole thing right here, 2 times the quantity x minus 1 squared. We've got one final thing to do, and what's that final thing, Buddha?
Shift the graph down.
Yeah, shift it down. Down, baby. 3 units, right? So shift it down 3 units, which is the same as saying subtract 3 from all y values. So again, my x values stay the same. Nothing to do there. Boom, 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 boom. And now I subtract 3 from all of my y values, which gives me 15, -1, -3, -1, 15. So these are now the points I graph, and those are the solutions. Those points represent some of the solutions. There's an infinite number of solutions to this particular function. So okay, so we got -2, 15. So let's plot that. -2, 15, -2, 15. There we go. And 0, -1. 0, -1 is right there. 1, -3. 1, -3 is right there. 2, -1. 2, -1. And 4, 15. 4, 15. Okay. So now I think I've got enough to get a quick sketch of this particular parabola. And there we go. Okay, it's skinnier than the previous one. And that's the stretching component. And the vertex has moved. Where did the vertex go? It was at 0, 0, and where did it go? What's the new coordinates of the vertex now? 1, -3. So notice the vertex shifted right 1 and down 3. Yes? Shifted right 1 and down 3. So can we identify the vertex of the transform function just by looking at this equation? Can you see the vertex in that equation? Okay, well, let's see where it is. Let's write that equation again. G of x equals 2 times x minus 1 squared take away 3. And here's my vertex, 1, -3. So where does the 1 and -3 occur? You told me you can pluck it right out of there. Where is the vertex? Yep, but are you going to always do the transformations in your head, or can you just look at this and tell me where 1 and -3 occur? Yeah, go ahead, Shane. Right, so 1, it comes after the subtraction sign, right? There's your 1. And here's your -3. So in general, we can write a new form of a quadratic. As we've said earlier, we're used to seeing the quadratic in the ax squared plus bx plus c form. Now we have a new form. Your book calls it the standard form of a quadratic function. You're going to hear me use this term off and on as well, the vertex form. So standard form, vertex form is similar. The other form is the general form, the ax squared. So this form of your quadratic, I think the book refers to this as general form. See, I'm a little backwards because I always refer to this as standard and this as vertex. But books do different things. So that's why, for me, you'll hear me sometimes refer to vertex because that's what this is going to tell me, the vertex. But I'll try to call it standard form like your book. Okay, so the standard form of a quadratic function has that form. And what transformations from the graph of y equals x squared does this form suggest? So so if you have this general, now we don't have a value for a, h, and k any longer. So in general, what has happened to x squared to get to here? You can pick on anything you want and tell me what kind of transformation has happened to x squared to get to that form. Okay. Pick any one and tell me. Doesn't matter which one you pick. There's 3 of them. I'll talk about all 3 of them. Logan? Okay, so we know there's going to be a shift horizontally, and I'm going to tell you why I'm not going to say to the right. Shift horizontally h units. So why am I not totally agreeing? I'm doing a little bit of editing of what Logan said. Why am I doing a little editing, Ben? Yeah, if h is negative, that becomes x plus h, right? If h has a negative value, so then it would be shifted left. So it's going to shift horizontally h units, and to determine which direction, it's going to go to the right. It's going to shift right if h is positive. And it's going to shift left if h is negative. And when h is negative, this equation is going to look like this. X plus h squared plus k. So when h is negative, that subtraction changes to addition. So that's how you'll always know if the x value of your vertex is plus or minus. If this subtraction changes to addition, then you know your coordinate, your x coordinate, is a negative number, a negative value. It's to the left. Okay, what else is happening here to x squared? We have shifting horizontally h unit, Ben? Yeah, there's a vertical shift vertically, K units. And if you look at the formula, it goes directly as it looks. If there's a positive value, because it's an addition here now, so if K is positive, you're going up K units. If K is negative, you're going down K units. Okay. And then we have to deal with that critic called A. That's got a few more situations. So what's A going to do? Generally, what will A do? Any value of A there is going to do what type of thing? Right. So we're going to have a vertical or vertical stretch or a vertical shrink. Right? So we're either going to have a vertical stretch or a vertical shrink, and that depends on the value for A. If A is a number that's bigger than 1, then we're going to be stretched. And I'm going to put that A in absolute value. I'm just thinking of the magnitude of A. And if A is a number between 1 and 0, the absolute value of A is a number between 1 and 0, this thing is going to shrink. So it opens a lot slower and it's a lot wider because all of your Y values have come down to be closer to the x-axis. So let's take a look at that for a second with the graphing calculator. So let's do a couple of graphs all at once. So let's say we do y equals x, say, squared, just a parent. And let's say we do y equals 10x squared. And now instead of 10, let's do 1/10, 0.1 x squared. So in one situation, x is 1, that's our parent. The next situation, x is 10, we should belong skinny. And then when it's 1/10, we should come way out. Okay, so let's take a look at the graphs. And let's change each of the ways we represent the graphs so you can distinguish them. Let's make this graph a bold line, and let's make this graph over here maybe dots. Do we have dots? Yeah, there we go. Okay, so let's take a look. Zoom 6 and see these graphs. Oh, baby. Okay, so you can see the effects now of the coefficient A on your parabola. Okay. Oh, no. What happened? I hate this order here. Oh, I don't want that. All right. Cut. Now, which order? You got to help me. Do I do that and then my camera? No, I've got to do my. Oh, there's my camera. Now I draw that up. Now I should be able. There we go. Okay. So here's just a little picture for your memory. Okay. So we've got. Here's f of x equals x squared. Here's g of x equals 10x squared. And one more color. Here's h of x equals 1/10 x squared or 0.1 x squared. Okay. So when A is a fraction in absolute value, it's a much wider opening. What happens if I change this 10 and this 1/10 to negative? Are the shapes going to still be the same as this really bold parabola and this really wide parabola? Are the shapes of it going to be exactly the same as when it's 10 and 1/10? If I change it to -10 and -1/10, will it still have the same shape? I see a yes, a couple yeses, same shape, but what's going to be the difference when I change it to negative? It's going to reflect which way? Over the x, right? So if it's negative, it's the parabola just goes downwards. So let's take a couple of these out. We don't want to get too crowded here. So let's just change 10x squared to say -10x squared. So it has exactly the same shape. It's just going to reflect or open up downward. So there's 10x squared and there's negative 10x squared. Okay, so if A is negative, our parabola opens downward. It's a sad parabola. So the standard form, this is our standard form, our vertex form, is really convenient for us because you can identify your vertex right away. Your vertex will always use these letters HK, just like the letters we used in the center for a circle. Okay, so if A is positive, the parabola opens upward. It's a happy parabola. When you're positive, you're usually happy. And when you're negative, you're usually not feeling very good. You're sad. It opens downward. Okay, and if the absolute value of A is small, it's a fraction, the parabola opens up wider, more flatly than when the absolute value of A is a large number. So now if we're going to try to do a quick sketch of a parabola, these are the key points, but we also need to find the x and y intercepts. Okay, so let's do a quick sketch of a parabola that's in this standard form so you can see how quickly you can actually look at the formula, look at the equation, and come up with a quick sketch. So let's identify the values for H, K, and A here. So someone want to help me identify the values for H and K? H and K is the vertex, and A tells me how the parabola opens. So what's the value for A here? -1. So I'm just going to throw it in. When I see that dash out in front, it's just like multiplying everything by -1. Okay. And now I can read right off of here the transformations that Shane talked about earlier, how we're shifting, and that will tell us what the values are of our vertex. So this tells me I shift 1 unit to the right. So I add 1, so H is 1. And up 4, K is positive. So 1, 4 is my vertex. That's a really important point to be able to graph, 1, 4. Okay, so let's put that first point in. Let's graph the vertex, 1, 4. Right now, 1 and 4. There we go. All right. Does the parabola open up or down? Down, because A is negative. A is negative, so I'm sad. So what do I know about this point, 1, 4, right now? What do I know about the value of 4? What do I know about that value? It's the highest y value, or the maximum y value, right? So right now I know 1, 4 is the maximum point. We call it the maximum point. The vertex is the maximum. And 4 is the largest value, or the maximum value. Okay, so we got a lot of information. We're almost there. We've got a couple of other key points to draw. So let's find the y-intercept. You find the y-intercept just like you find any y-intercept. You let x equal 0. So if you let x equal 0, everything, let's see what happens here. X equals 0, so we've got negative, and inside the parentheses we got -1 that's squared, so don't lose your negative signs now. You got the negative on the outside, which is -1 multiplying whatever's being squared, then you add 4. So we've got -1 squared is 1. We get -1 times 1, that gives us a -1 plus 4, so we get 3. So when x is 0, y is 3. So we put a point right there, 0, 3. Okay. Now, based on the symmetry of your parabola is going to be able to be folded across a vertical line called your line of symmetry that goes directly through your vertex, right there. There's your line of symmetry. So you can fold this parabola across that line, and the points on either side match each other. They're mirror images. So our line of symmetry here has the equation x equals 1. Because that's a vertical line, x equals 1. Everything on that vertical line has an x coordinate of 1. So once you find your y-intercept, you can get its matching its partner on the other side of the line. Because look, you've got to be at exactly the same height. Here's the point 0, 3. How far from that line right here, this line x equals 1 is 0, how many units to the left is it from the line x equals 1 if you're at 0? 1. So now instead of going to the left 1 unit, you just go to the right 1 unit and put another point right there. You've got a matching point. It's called 1, 3. So once you find your y-intercept, find its partner also. That just helps you get another point to get a pretty accurate sketch of your graph. So you've got your vertex, 1, 4. You've got your y-intercept, 0, 3. And then you've got its matching mirror image on the other side, 1, 3. So now if you find your x-intercepts, you got 2 x-intercepts here, and you got enough to do a really quick sketch. So yeah, it should be 2, 3. Thank you. I put it in the right spot, but I didn't label it correctly. 2, 3. Thank you very much. All right, so now we got to find the x-intercepts. How do we ever find the x-intercepts for any particular equation or graph? How do we find the x-intercepts? Set y equal to 0, so f of x is 0. And so now I have a quadratic equation to solve. So I set that equal to 0. And I solve for x. Okay, so let's review all of that. Just going to write that there. Its partner using symmetry is 2, 3. Okay, so we got negative parentheses the quantity x minus 1 squared plus 4. So I want to solve for x now. So you got a couple of choices. You can square this whole thing out using FOIL, or you can just set this up and take the square root of both sides once you isolate your square term. So I'm going to subtract 4 from both sides, and I get negative 4 equals negative 1 times x minus 1 squared. My goal is to isolate my squared term, squared term. Okay, so right now it's got a negative 1 multiplying it, so now we want to divide both sides by negative 1. And that gives me 4 equals x minus 1 quantity square. So I've got a perfect square on the right side and a constant on the left side. So I'm just going to rewrite that like this. And anytime I have something squared equal to a constant, I square root both sides. And I remember I have a plus and minus. So x minus 1 equals plus or minus 2. And now I have two equations to solve. X minus 1 equals 2, and x minus 1 equals negative 2. And I solve those baby linear equations. I get x equals 3 and x equals negative 1. So there are my two x-intercepts, 3, 0, and negative 1, 0. So now I go up to my graph and I plot those points, 3, 0, and negative 1, 0. And then that's enough for me to do a nice quick sketch of my transform parabola. Okay? So those are the steps. They're all there for you. So anytime you have to sketch something in your homework, these would be the steps you follow. Are there any questions on this at all? What steps you would follow if you have this standard form where your vertex is like saying, here I am, just plot me right now. I'm right here, you can see me. Right? And A saying, you know if I'm up or down. Then you got to do a little work to find the vertex and the x-intercepts. Okay? Any questions at all before we move on? I don't want to move on if there's something hanging around bothering you about anything we've done so far. All right, so we're done with the first page. Let's take a look at the second page. The second page says, okay, how would we actually change this function if it was in the standard form or the vertex form into the general form that we're used to seeing for a quadratic function? What would you actually do to this form to transform it into an equivalent form that was in polynomial form like this, where you had a bunch of terms? Quadratic term is this term. Remember, terms are the adding and subtraction pieces of an expression, that's quadratic because it has a square. Your linear term, because the exponent there is 1, even if we don't write it. And then this is your constant term. So how would we take this form and make it look like ax squared plus bx plus c? What would we do? Huh? Yeah, do it out. What does do it out mean? So you basically just say, okay, that minus is a -1. To square x minus 1, I do x minus 1 times x minus 1, and I add 4. Well, your order of operations says all of this stuff has to happen first, and then you get to add 4 to the end. So we have a -1. We're going to square x minus 1, which is x squared minus 2x plus 1. Okay, and then we change all the signs. When we multiply by -1, we change all the signs of everything in there. So we get -1x squared plus 2x minus 1 plus 4. And then the last two terms we can combine. The -1 and 4 becomes a plus 3. So this is now what it looks like in the general form. So let's compare them and see how, if anything, we can go from one to the other, if we can grab anything from one form and get to the other form. Okay, so here are our two forms. Let's take a look at sort of the pros and cons of each one. Okay, is there anything that's the same, any letter that's the same in both of them? Well, one of them has an HK and the other one has a B and a C. And the H and K don't seem to correspond at all. What do you notice, Cameron? You had raised your hand. Oh, not to answer? Oh, okay. Is there anything that's the same, whether you're in this standard or vertex form or the more general form of a quadratic? Mary? A never changes. So if you know A in one form, A stays the same in the other form. So over here, if you stuck it in, there's A. A is -1. And here, A is -1. No problem. Stays the same. Okay? So what else? What would be, again, what's the nice thing about this standard form or vertex form? They both tell you how the parabola opens. What is the advantage of this form right here? You can get your vertex right away. Boom, it pops right out. Your vertex is 1, 4. So that's a neat thing. Okay. Can you get any point off your graph right now from looking at this general form? Any point pop out at you? Yes, absolutely. Shane, you are just becoming a math geek this semester, huh? There you are. Just like with your y equals mx plus b, that final constant term is always your y-intercept, because when x is 0, the x squared term disappears and the linear term, your x term, disappears. So right here, that's what you can get out of that function, is you can get your y-intercept. So you can get a point from either form, a y-intercept from one form and your vertex from the other form. Okay? And then you got to do some work. You got to find your x-intercepts, and you got to do a little work. But as you can tell, this vertex is kind of a key point. It's that turning point, right? That turning point we've talked about. So we've got to be able to take a function that's in this form and make it look like this form, the vertex form, because that's really the key thing. Well, your book shows you all the mathematics involved to getting there. It's completing the square, just like the form that the procedure that they use to actually come up with the quadratic equation. So if you like that stuff, it's in your book. They do a fabulous job explaining it. All we're going to do is we are going to actually use the result of that particular proof. So if we want to take this form of a quadratic equation and we want to change it to that form, or we want to be able to get the same information. If we start out here, we want to know, how do I find my vertex? I can find A. A is the same in both. How do I find my vertex? Here's the formula right here. H, remember, is the x value of your vertex. I use x sub v, x value of vertex. That's H. All you have to do is take negative b over 2a. Maybe that looks familiar to you, the opposite of b over 2a. That comes from your quadratic formula. Notice it's this first term right here in your quadratic formula. Because from your vertex is your midpoint between your two zeros or your two x-intercepts. So that's the very first part of your of your quadratic formula. That's how you find your x coordinate or your h value, and then to find your output, you plug it back into your function. So you take the function and you say, okay, I'm going to put in my x value, and there's your k value. So there's your hk. Now, it looks a lot harder than it is to actually do, so let's do it with some numbers. So here's a quadratic function. It has this general form, and we want to change it to the standard or vertex form. So we want to be able to change this so it looks like a times the quantity x minus h squared plus k. So we want to go from this form to this form. Okay. So right away we know what a is. What's a going to be? -1, because it's -1 right here. Here's your a. It's the number that multiplies your x squared term. It's going to be the same over here. Okay, we got that part. Now we got to figure out what is h and what is k. Well, h is the x coordinate of your vertex, and that's -b divided by 2a. So what's b in this expression right here? -1x squared plus 4x plus 1. What's the value for b? 4. Right. It's the coefficient of your linear term right there. So I take the opposite of 4. We've already identified a is right there. A over 2 times -1. So there's my b, there's my 2, and there's my -1. And that gives me -4 divided by -2, which is 2. So now I know the x value of my vertex. I know it's 2. And now I've got to find my y value. And how do I find my y value? I just plug it in. It's f of 2, f of -b over 2a. So I put 2 into my formula. So everywhere I see an x, I put a 2. And I get -4 plus 8 plus 1 is 5. So now I know the y value of my vertex is 5. So I've got my vertex. That's fantastic. And now I can write out this, I can write this quadratic function out in the vertex or standard form. There I am. So once I have that form, I know what's going to happen to my vertex 0, 0. I know how I'm going to shift it. I'm going to shift it to the right 2 and up 5. I know my parabola is going to open downward because a is negative. I can look at this original form, look right here, my original form, and get my y-intercept just like that. So if you have these two forms, you can get your vertex, you can get your y-intercept, you can get whether it opens up or down, and once you have your y-intercept, you get the point that it's symmetric to. So you can get 3 points and know how your parabola opens, and that's before you even find your x-intercepts. So we know the parabola opens downward because a is negative. We know our y-intercept is 0, 1. So let's do some graphing. 2, 5, 2, 5 is my vertex. So 5 is my maximum value. 5 is the maximum value in my range, in the range of my function. Okay. I'm going to be going down. I'm sad. And I'm going to plot 0, 1. Here's 0, 1. Where's my line of symmetry? Where's my line of symmetry? My vertical line going right through x equals what? Right through my vertex, x equals what? 2. So I do a vertical line straight down. And once I do that, that helps me find my mirror image, the point that's symmetric to my y-intercept. Since 0 is 2 units to the left of my vertex, its partner or mirror image is going to be 2 units to the right. So at 4, 1, I'm going to have another point. That's the mirror image. So now I just have to find my x-intercepts. Okay, so let's do that. That's not a problem. We're going to just set my equation equal to 0. All right, so let me give myself a little space here. Okay, so I set my equation equal to 0. My equation is negative 1x squared plus 4x plus 1. You might say, why am I using that form? Because that's how I'm used to solving quadratic equations, with it in the form ax squared plus bx plus c. Now I look at that and I say, I can't factor that. If you can't factor a quadratic, it tells you that your roots are irrational numbers. They're not going to be nice, pretty rational numbers. So you have to use your quadratic equation in order to find the x-intercepts or the roots or the zeros. That's all, those are all names we have for x-intercepts. All right, so let's do the quadratic here. A is negative 1, B is 4, and C is 1. So x equals the opposite of b plus or minus the square root. B squared is 16 minus 4 times negative a times c, all over negative 2, which is 2a. So notice I'm not going as slow as when we first covered this about 4 weeks ago, because we've already done this. 6 plus 4 over negative 2, negative 4 plus or minus the square root of 20 all over 2. We can simplify the square root of 20. Square root of 4 times square root of 5. Square root of 4 is a perfect square, so that's 2 square roots of 5. So x equals negative 4 plus or minus 2 square roots of 5 all over negative 2, which is 2 plus or minus the square root of 5 when you simplify it. So what do your two x-intercepts look like? 2 plus the square root of 5, comma 0. 2 minus the square root of 5, comma 0. Those are them exactly. But guess what? We have to plot them. So we are going to have to get an estimate for these. So let's estimate their values. And in order to do that, we have to take out our calculator, because I don't know 2 plus the square root of 5 off the top of my head. So I pull that out. Come on. Is it already? It's hiding here somewhere. I hate when this happens. Come on. Where'd you go? Any help? Anybody? Let me close it and then maybe close my window and then I'll get it again. There we go. It's always the answer. Shut it, turn it off and turn it back on. Okay, so let's quit. Let's clear everything, and we've got 2 plus the square root of 5. What's that come out to be? 4.23606. It's going to go on forever and ever, so we'll just say 4.2. So we'll estimate this to be 4.2 comma 0. And then let's do 2 minus the square root of 5. Negative 0.2 comma 0. So basically the width of my little pen up here on my symposium is going to really affect this. So I want to get real close to 0 on this side, and then 2.3 is about right. Oops, wait a minute. 4.2, I was going to say, it can't be inside there. That was, oops, so can I do an undo here? Yes. So 4.2, it's kind of like right there. Oh, okay, so you just connect these dots, and there you go. There's your graph. So sometimes you get yucky x-intercepts. Sometimes you get no real number intercepts. If you got a negative number under the square root sign, that means your parabola never crosses the x-axis. Okay, so sometimes that happens. You can cross your x-axis. You can have, at most, 2 x-intercepts. That's the most number you can have. At most 2. You could have 2. You could have 1, like with x squared. It only comes down and touches it once. Or you can have none at all if the parabola looks something like this. It doesn't cross the x-axis at all. So 2, 1, or 0 x-intercepts. Remember, another name for x-intercepts when we're dealing with functions is zeros. It's the zero of the function. It's the value of x that makes your function equal to 0. So if you put this equation into your calculator, let's clear everything out of here. Can someone read me the value of the equation so I don't have to scroll back through? What was it, negative 1 x squared? Was it plus 4x? Plus 4x plus what? Plus 1? Okay. So if you graph that, and you just do a real quick graph of it, zoom 6. There you go. And let's suppose you just wanted to check your work and you wanted to find the x-intercepts, okay, which we just did. You do second calc, and you go down to where it says 0, because remember 0 is the same as your x-intercepts. So you go down, you say, okay. So it says, tell me where the left bound is. So you know your x-intercepts right here, and it's pretty close to 0. So if you pick any number to the left of, say, -1, -1, or to the left, so you just say, okay, enter -1. That's going to be my left boundary. Then pick any number to the right of that, but you don't want to go beyond this 0. So I just say, okay, 1. And then I say, guess. I'll let you guess. And there's your -2.3606. Okay, that's 2. Take away the square root of -5. That's the estimate. Then to get your other 0, you have to hit second calc again. You go down to 0, and you play the same game. You take a number that's to the left of this x-intercept, but doesn't go across here. So 1, 2, or 3, you have a choice. I'm going to pick 2. And then you take a number to the right. So I'm going to pick 7. And then I hit enter again, and there's my 4.236068, or 2 plus the square root of 5. But guess what else it tells you? Vertex. Oh. Second calc, it's the maximum point on that parabola. What's to the left of that vertex? 0 is to the left. What's to the right? 4. Let the calculator guess. And there you go. It's thinking 2, 5. 1.9999 is the same as 2. Okay, because notice, it looks like see how it looks like a horizontal line right there? It's because the value it took to the left and right, and then it just connected those. It didn't take any intermediate value. So when you see something like that in your calculator, you call it 2, 5. Okay, so that's how you could use your calculator to get all of the information we just got. Okay, let's see. So here's a spot that sometimes students can get a little like, how do I get the equation if I have the graph? You just showed me how to get the graph if I had the equation. How would I get the equation from the graph? Well, I just want to remind you that you've done this before for straight lines. If I give you 2 points for a straight line, any 2 points, 2, 5, 3, 9. If I give you those 2 points, the first thing you do is you find the slope. You find the slope and you plug it in. Then you have to find B. So once you find the slope, you have to find B, and the way you find B is you pick one of these points. And maybe you put 2 in for X and 5 in for B, and your slope in this particular case is 4. So once you have the 4 out in front of the X, and you put 5 in for Y and 2 in for X, then you solve for B, and you get your equation. That idea works all the time, whether you go from a linear equation to a quadratic equation to an equation that may have a cubic in it or an exponential equation. It's the same idea used over and over. So let's see what we have to get in order. Let's do the vertex or the standard form first. So we have f of x equals a times x minus h squared plus k. So just like you know how to find the slope if you have 2 points, change in y over change in x, can you look at this picture and tell me what h and k is from looking at the graph of the vertex? Well, I'm asking you, can you tell me what h and k is? What's h, Logan? And what's k? Right. So look, we're almost done. Wow, this is pretty cool. So this is just like putting, say, the slope into your y equals mx plus b. You've got one letter to solve for, folks, a. So you need to know an x value and a y value to plug into that equation, and then you can solve for a because you only have one constant left to solve. Do we know a y and an x, or an x and a y? Do we know another point other than the vertex on this parabola? Yes, no? And what point? Well, we know two, right? So pick the one that's the easiest. Anytime x is 0, that's really easy for your arithmetic. So now pick a point, any point. We happen to have two to choose from, 0, 23, or 6, 23. So let's plug 0 in for f of x, 0 in for x, and 23 in for f of 0, because when x is 0, my y value is 23. So we get 23 equals a times, now I plug 0 in for x, and now I can solve that equation for a. So I do what's in parentheses first. I get a -3. I'm going to square that. I get 9a plus 5. Subtract 5 from both sides. Divide by 9, a is 2. I'm done. So the equation for my parabola is 2 times x minus 3 quantity squared plus 5. That's my standard form or vertex form. If I put it in my other form, it's 2 times x squared minus 6x plus 9 plus 5, 2x squared minus 12x plus 18 plus 5, 2x squared minus 12x plus 23. That matches that point. We can see that it's the y-intercept. So those are the two forms, your standard form or vertex form, and then the general form of a quadratic equation. So you can go from one to the other. You can look at a graph and also figure it out as well, how to get the equation from the graph. You have a lot of power and ability right now. Okay? So the last thing we have to do is be able to deal with this idea of maximum values and minimum values. This is a big application of any quadratic function. So let's see where we are. So number 9 on the bottom of page 2 says, what key feature of a quadratic function marks its maximum or minimum value? What's the key feature that marks either the maximum or minimum value? The vertex, yep. Okay. So we're going to be doing some problems that just deal with the vertex. So without graphing, determine whether this function has a minimum value or a maximum value. So here's our function, 4x squared minus 16x plus 1,000. Woo, baby. Big y-intercept, 0, 1,000. Okay, so is this function going to have a minimum or a maximum, and how do you know? Mary? And how do you know that? A is positive, right. A is equal to 4. It's positive, so this parabola opens upwards, so my vertex will have a minimum value. Be the minimum value. Okay, find the minimum and maximum value and where it occurs. Where it occurs is h, or your x value, and the minimum, in this case, the minimum value is your k value. Right, so this is the x value of your vertex, and this is the y value of your vertex. So let's find out what that is. The x value of your vertex, or h, is the opposite of b over 2a. That's how I always find it. Opposite of b over 2a, which is 16 over 8, which is 2. And now to find my y value, the value of my function when x is 2, I say, what is the value of my function when x is 2? So I go ahead and plug 2 into my function. 4 times 2 squared minus 16 times 2 plus 1,000. Okay, this is going to be my k value of my vertex, or my minimum value. Here's where my minimum value is found, right here, when I find the y value, the function at value evaluated at 2. So I get 16 minus 32 plus 1,000, and that gives me 984. So the minimum value of my function is 984. So my range is going to start at 984 and go to infinity. That's my range. My domain, as I know, is always all real numbers. Where does it occur? It occurs at x equals 2. Yes, because the only way to find k is to plug this value of x into your function, because your function depends on x, right, Shane? So we got to find x first, because everything else depends on knowing what x is, okay? Any questions on this? Okay, we have 2 application problems to do, and we've got 9 minutes to do it. What we just did here is how you do number 11, except number 11 has an application. It has a context. It has a story. So here's a story. We're going to be looking at the height of an arrow, f of x in feet. So here's the height, f of x. And after we shoot the arrow, it's going to have both a vertical height and a horizontal. So this is the horizontal distance. And both of these are measured in feet. Okay. So I'm shooting my arrow. How far above the ground is my release point? How far above the ground is my release point? 5, right? It's your y-intercept right here. So this release point is 0, 5. This arrow is going to go up, reach some maximum value, and then come back down to Earth. Okay. So what I'm trying to find is the maximum height. The maximum height occurs anytime you see maximum, you know you're looking for the k value of your vertex. K value of vertex. How far when does it reach its maximum height, and then how far is it? When does this occur? That's your h value. And as Shane pointed out, you always have to find your h value or your independent variable here, x. So h is the x value of your vertex, and k is the y value of your vertex. So let's find the x value of our vertex, and then we can find the height. So the x value of my vertex is the opposite of b over 2a. B is 2, negative 2 over 2 times negative 0.005, which is negative 2 over 2 times negative 0.01, which is negative 2 over negative 0.02, which is the same as 2 over 0.02, which is the same as 2 divided by 200ths. This is without a calculator. 2 times 100 over 2 is 100. So I don't have a calculator, but that's how I would do it in my mind. So I know 100 feet from when it leaves the bow, my arrow is going to reach its highest point, and to find that, I throw f of 100. I evaluate my function at x equals 100. So again, you all have calculators at your seats. I don't. So I just plug 100 in here for x. And I get negative 0.005. 100 is 10 squared. So when I square that, that's 10 to the 4th. That's 10,000 plus 200 plus 5. This is negative 5 1,000ths, right? You can do it on your calculator if you want. I'm just doing it this way because I don't have a choice. And 1,000 goes into 10,000 10 times. So I get negative 50 plus 200 plus 5. So what's my maximum height going to be? 155, yes? Did I do that correctly? Or did I screw up somewhere? I don't think I got that same answer in my first class. Where did I screw up, Mary? Where? Where did I multiply? Oh, I multiplied by 2 twice here. Oh, right. You know, I knew the answer from doing this at the, it's over there on the board, by the way. I did this in my first class, and I knew I wasn't right, but I really had faith that one of you would find out where I was. I knew I was wrong back here, but I couldn't find it, so I kept going. So it's 200. It occurs at 200. And so you change that to 200. And then you say, find the value, your maximum height when x is 200. So this all becomes 200. This becomes 40,000. This becomes 400. 40,000, 400. This is what? What is the final answer? 205, right? I knew I was wrong. I just didn't know where I screwed up. Okay, so 205 is the maximum height that this arrow reaches. Maximum height. Okay. So again, it's just what we just did a minute ago, except for it has a story and a meaning behind it, which is really the reason why we use quadratic functions to begin with. They all have applications. Some of you actually found data in your second project that a quadratic, and I think I wrote on a couple of your papers, a quadratic might be a better model. If I wrote that on your paper, I'd love to see the data again for what we're going to do next week. So if I wrote that on your second project, just remind me what your data was. Okay, and the final thing is maximizing area. And this is like one of your typical word stories or story opportunities you would have had along the way. You've got some kind of river. Oop, I better make it blue. And you want to construct, huh? A river of lava, you're right. Yeah, I guess I don't like think of geology. I think of kind of like rivers by my house. So, okay, all right. So there's my pen, and you can put little oinkies in there or little babas in there, whatever you want. There's your corral. You have 400 feet of fence. What geometric measurement does that 400 feet represent? What geometric measurement do we call that 400 feet of fencing? Perimeter. You knew it had to be one of them, right? So this is the perimeter. So if I let x be the length of the fence, that's say perpendicular to the river, then right here I'm going to mark those x, and that's going to be in feet. So how do I represent the length of the fence that's parallel to the river? With an expression with x in it. So if these two lengths are x, what's going to be the length of this piece right here? 400. I got 400 feet to begin with, and I'm going to use x feet here and x feet here. So 400 minus 2x is what I'm going to have left. So that's how I represent the side that's parallel to the river. So if x was 50, I'd have 50 and 50 is 100. I'd have 300 feet here. 400 minus 2 times 50. I have 300 feet left over. That's why it's subtraction. Okay, so I want to maximize. You see that word, or largest. Largest means you're going to try to find the maximum value of the area, the largest area possible. Okay, so when you see the word largest and you're dealing with quadratics, you want to find the maximum area. So we're going to have a function in terms of x. It's going to be the length times the width. And now area is a square measurement, so that's why a quadratic is the appropriate function here. And so we say, okay, let's make this look like a quadratic in the form that we're used to seeing. And if I put it with my square term first and my linear term second, so I can identify a and b, that's what it looks like. And now to find your maximum area, you say, okay, what's the value of x at this maximum area occurs? So that's the x value of my vertex. That's negative b over 2a, which is 400 over 4, which is 100. So you can either plug that back in, find a of 100, and do your math, or you can go back to your picture and go like this. It's much quicker. If x is 100, then I have 400 minus 200, which is 200. So my area is 100 feet times 200 feet, which is 20,000 square feet. So that's my maximum area. And I'm sorry I kept you 35 seconds late. Have a great couple of days. Know that I'm around. If you have any last minute panic studying for your test, I'm always around. just let me know and I'll see you. And I need to just get this recording and then before we